Hello students, welcome back to this new session on mathematics for the third semester students for the subject 18mat31. I'm your mathematics teacher from AITM. In this session, I'll be just continuing the same Laplace transform which we have studied in the past two sessions. And in this session, I'm going to just derive some Laplace transform of some standard functions, okay? As I have written here, and you can see it on your screen, okay? So here are some important functions we need to work for their Laplace transform, and those can be the formulas for your coming problems, okay? So you need to memorize all these small transforms of some standard functions so that you can use them in your problems to work, okay? So here are with the first this, okay? That is, find the Laplace transform of, right here, the Laplace transform of e to the power at, where a is any real or complex number, or you can say it is constant x number, okay? You can just say it to be constant also, that is constant, okay? Constant, that's one thing, okay? It is constant, okay? You need to work for the Laplace transform of this. Let's work for that. Solution, okay? Solution goes as the Laplace transform of e to the power at we are working for, is it? Okay, now as per the definition, what does the definition says? Let us write. Okay, first we will not do this, okay? We will not write this. We will just say what is the Laplace transform of f of t first, okay? First we'll write the Laplace transform of f of t, okay, so that it will be helpful. Okay, so it is integration from 0 to infinity. Write the basic definition, e to power minus st f of t dt. Now in this case we are working for e to the power at, that is the Laplace transform of e to the power at. So it will be equal to integration from 0 to infinity e to the power minus st, and f of t here in this case it is e to the power at. So e to the power at comes over here dt. Is it? Now I can rewrite this as integration from 0 to infinity e to the power. Now I can take it as minus st plus at by using the laws of indices. Is it? Or this is equal to integration from 0 to infinity e to the power. I'll take minus t common from here, okay? Take minus t common. So what you are left with? S minus a inside the bracket or no? Right? dt. Now integrate this. So when you integrate this, I'll just continue it here, just have a look. So when you integrate this, integration of this is e to the power minus t into s minus a. Now you are integrating with respect to t. It means the coefficient is s minus a, and that is constant for you. That divided by s minus a, yes, with negative sign. You can write minus over here, okay? With limits from 0 to infinity. Now as usual, when you put t as infinity over here, yes, what is the integration of e to the power ax dx? It is nothing but e to the power ax divided by a, or no? In place of a, the constant, the coefficient of x, you have s minus a over here, right? And if it is minus over here, integration of this will be minus e to the power minus a x divided by a. Okay, so that negative sign is also there. So integration from 0 to infinity you are going. Now let us put upper limit and the lower limit. If you put the upper limit, it becomes e to the power minus infinity, like in the previous problem we had solved in my previous session, okay? So it is e to the power minus infinity. When e to the power minus infinity appears, definitely it will be 0. So the upper limit is 0, minus 0 you get, minus the lower limit. So the lower limit is minus, this is the upper limit, minus the lower limit is you are putting t as 0. So when you put t as 0, e to the power 0 it will come, and e to the power 0 is 1 divided by s minus a over here. This is the lower limit, upper limit minus the lower limit, or this is equal to 0 is as it is, 0 is 0 only, then 0 minus into minus, it becomes plus 1 divided by s minus a. That is, the Laplace transform of e to the power at is 1 divided by s minus a. This is the solution. Okay, I hope it is clear to you. Let us work for some more standard functions Laplace transform. Okay, now let us work for the Laplace transform of cos hyperbolic at, where a is again constant. Okay, a is constant. Okay, so as per the definition, once again you have the Laplace transform of f of t to be integration 0 to infinity e to power minus st f of t dt. Okay, so what should be the Laplace transform of cos hyperbolic at? Now in place of f of t you need to replace by cos hyperbolic at. So it is integration from 0 to infinity e to power minus st cos hyperbolic at dt. Okay, now how to work for that hyperbolic function like this? So it's very simple. You know the basic definition of cos hyperbolic at. What is cos hyperbolic at? In exponential form, definition, it is equal to e to power at plus e to power minus at divided by 2. So let us use this definition of cos hyperbolic at over here. So what do you get? Integration 0 to infinity e to power minus st. In place of cos hyperbolic at, we need to write this expression e to power at plus e to power minus at over 2 dt. I hope it is clear to you. Now multiply this e to power minus st to each of this. Okay, divided by 2. I'll take that half outside because it is constant outside the integral sign. It has nothing to do with the integration. Get it outside of the integral sign. Integration 0 to infinity e to the power t, as I told you, okay, you just take that st plus at you will get after multiplying these two by using laws of indices plus e to power minus st minus at dt. This is what you end up with. Okay, now in each of these two things I will take minus t common. Okay, so 1 by 2 integration from 0 to infinity e to the power, you take minus t common, you will get s minus ac, like in the previous case when we were working for the Laplace transform of e to power at. Okay, and you can directly solve it also. Actually you need not work for that. It is nothing but if you separate it like this, like you can just see this half I will take outside. You can do it directly also. You need not work exactly like this. Directly within 2 steps you will get your answer. However, if you just see this, see in detail this, it is nothing but this dt, this take a bracket plus if I split it, okay, using this plus sign, integration from 0 to infinity e to power minus st into e to power minus at dt. Now as per the definition, in place of f of t, just compare this with this. Okay, you find that this is nothing but the Laplace transform of e to power at, and this integration is nothing but the Laplace transform of e to power minus at. Is it not? You can solve it like this also. Okay, and previously you have already solved the Laplace transform of e to power at. Okay, so it is nothing but half Laplace transform of e to power at is, you have solved it in the previous problem itself. So it is 1 divided by s minus a plus Laplace transform of e to power minus at. In place of plus a you are writing minus a, it will be s 1 divided by s plus a you get. That is Laplace transform of e to power minus at. It is nothing but 1 divided by s minus of minus a it becomes. Is it not? So it will be 1 divided by s plus a. So we can substitute it directly. Okay, or else this is another way of solving it. Okay, and then you take the LCM, then simplify it. If you take the LCM, it will be s plus a plus s minus a over 2 times s square minus a square. Is it not? Because s plus a into s minus a, that is a minus b into a plus b is a square minus b square. Here in this case it is s square minus a square. So now when you simplify this, a and a will get cancelled. You will get 2s, and just continue it here only. So you get 2s divided by 2 times s square minus a square. Now 2 gets cancelled, or it is just 1 minute. Okay, so you get it as s divided by s square minus a square. So this becomes the Laplace transform. This is another way to solve it. Okay, but if you don't want this, you can do it this way also. Okay, I am showing you both. Whichever is easy for you, you can easily opt it. So plus a you get dt. Okay, now when you integrate this, it is half. Integration of this is e to power minus st minus s into s minus a divided by minus sign s minus a plus integration. Here also you will get minus here because the integration of this is minus. Okay, just see that. this from the limit 0 to infinity. Now the upper limit for both the terms will be 0 because e to power minus infinity is 0. So upper limit for both the terms is 0 and you can solve it. Either this goes very simple, very easy. You have to go for about 3-4 steps. Directly you can apply the previous formula and solve it. And it is not difficult also to remember the previous formula, okay, for the Laplace transform of e to power at and e to power minus at. Yes, so you can easily solve it. Otherwise you can do it this way also. There are many ways to go for that. Then however the upper limit is 0, just see half. Upper limit is 0, here also the upper limit is 0, minus, the upper limit for both the terms is 0, minus the lower limit, 1 divided by s minus a with negative sign, again 1 divided by minus s plus a, like this. Again when you solve it, already I have solved this part, now it is nothing but half 1 divided by s minus a plus 1 divided by s plus a. Now this part I have already solved it here, it is nothing but 2s, okay. After solving, like how I have done here, it will be like this. Either you can go it this way or you can go it solve. Whichever is easy for you, you can follow, okay. So this is the Laplace transform for cos hyperbolic at. Now similarly, I want to give you one problem as homework, okay. You can work for the Laplace transform, take down it as homework for you. Homework for find the Laplace transform of sine hyperbolic at. Same formula, only thing is that I'll let you know about it. Find the Laplace transform of sine hyperbolic at. Work for this, okay. Only thing is that you are going to use the sine hyperbolic at as e to power at minus e to power minus at divided by 2. Only that here you get minus sign. The rest every solution will be same, and in place of s over here you will end up with a divided by square plus a square. Only that is the difference. Rest everything is same, okay. Work out this for this at home on your own, okay. That is, you are going to use this formula and work, okay. Continue in my next session. Thank you.